We're gonna have to make a video about this cake. Why does this cake look like this? It's not molded, it's not designed by humans, this is just the natural pattern that appears when you bake it. This dessert is called tiger skin cake, and it seems to have originated in southern China, most evidence points to Hong Kong, where it's served in the form of a Swiss roll. Although its name comes from the patterns on it, tiger is not the first thing I thought of when I saw this cake. I thought it looked like maybe a brain. Right after that, another animal came to mind though, and that's a pufferfish. Several species of pufferfish and zebrafish have kind of meandering stripe patterns that are very similar to this cake. What's interesting about this, though, is that we understand how these patterns on fish skin develop, and the same mechanism appears in other contexts in biology, in chemistry, and even in condensed matter physics. They're called Turing patterns. That's the same Turing whose name now appears in phrases like Turing machine and Turing complete. Alan Turing is famous for his advances in information theory and cryptography during World War II, but in the last few years of his life, which unfortunately ended prematurely, Turing wrote a paper that has since become a seminal work in developmental biology. If nothing else, I think that's a good demonstration of how interconnected all of these fields are. The basic idea of Turing patterns is that if you have a system that undergoes diffusion, as well as some kind of reaction to change the amounts of whatever chemical or particle you're interested in, complicated patterns can form by themselves. Depending on the details of the system, this could be spots, stripes, spirals, or something that I personally think looks a lot like our tiger skin cake. Because these reaction-diffusion systems follow such simple rules, we can easily simulate them to make Turing patterns ourselves. For this example, I'll use the Gray-Scott model, which assumes that there are two chemicals, or morphogens as Turing called them, and two simple reactions that can happen between them. 1A and 2B can combine to make 3B, and B can become some other chemical that we don't care about. Also, we'll assume that morphogen A is being fed into the system at some rate. We'll make A blue and B yellow, so the color of a pixel on our screen will represent the concentrations of A and B in that region. For each pixel, or imaginary square in space, we can say that the change in concentration of chemical A over time is equal to the amount of A that enters or leaves because of diffusion, which we just know from physics, minus the amount of A that turns into B because of reactions. We're writing this as A times B squared because the reaction is more likely when the concentration of chemicals is higher. Then we add the amount of A that gets fed in. For morphogen B, we say that the concentration over time again equals diffusion, plus the amount of B that's added because A turned into B, minus the amount of B that turned into some other chemical. Multiply both sides by the change in time, and you have an equation that tells you the colors of each pixel over time. To get our Turing pattern, I made an arbitrary picture that represents some blobs of chemical B in an ocean of chemical A, and then we just let these equations run. Here's what we get. I think that's so cool that you can get such complex patterns from such a simple picture and two small equations. I should also mention now that because of the similarity between the discrete 2D Laplacian operator, which we use to represent diffusion, and the kernel used for sharpening filters, you can make similar patterns without any code, just by repeatedly applying a blur and a sharpening filter in Photoshop or something like that. Researchers have been able to demonstrate that reaction-diffusion models really do explain some of the patterns that we see in nature. In zebrafish, two pigments that are responsible for the colors of their skin, melanophores and xanthophores, interact in ways that satisfy the requirements to make Turing patterns, and that's where their stripes come from. We can simulate the pigments, and we get pretty similar patterns. So I guess that's what our plan is for this cake. We identify components of the ingredients that react with each other during baking. Then if we find something that looks like a reaction-diffusion model, we can simulate it, and hopefully it looks like the cake. I'm not a baker, or a food scientist, or even a chemist, so I don't really know how I'll go about doing this, but I do know from recipes that the tiger skin is made by beating egg yolk with sugar until it becomes light, mixing in cornstarch, spreading it flat on a baking sheet, and letting it bake. So whatever the morphogens might be, they have to be something found in air or those three ingredients. Let's do it. I feel like this isn't going anywhere. There are just too many things in food, even in just these three ingredients, to pinpoint what it is that causes some parts to rise and brown more than others. Once I started to get discouraged in my search for morphogens, I thought it might be inspiring to watch the cake bake again. It wasn't until then that I was watching this baking video by Michael Lim that I realized that the cake starts to form patterns long before any browning happens. In fact, it doesn't really look at all like a chemical phenomenon. It looks more mechanical, kind of like my hand. The patterns that we're seeing on the cake are just wrinkles, like my fingers after soaking in water. It's not a reaction-diffusion system, it's just physical folding. So I guess it's not a Turing pattern because it's just wrinkles. Or are all wrinkles Turing patterns? We can't deny that it looks like patterns on animal skin, that's what the cake is named after. Why do wrinkles look like this anyway? Before we get to the solution of why wrinkles look like they do, we need to know why they're here in the first place. When your fingers soak in water, the stratum corneum, the layer of dead cells on the outside of your skin, absorbs the water through osmosis because of the concentration gradient. Coincidentally, that's the same reason that morphogens diffuse. The dead cells swell and increase in surface area, while the tissue below stays the same volume, so your skin wrinkles to accommodate. When your fingers are in salt water, the concentration gradient is less dramatic, so it takes longer to get wrinkles when you're swimming in the ocean. There's just one problem with this. It's wrong, or at least it's not the only reason for the wrinkling. What I just explained is a common rumor, and it's the explanation I was always told in school, and you have probably already written a comment correcting me. Although this explanation is convenient and logical, researchers have been able to demonstrate for a long time that when nerves aren't functioning properly, your fingers and toes don't wrinkle. The wrinkles are an intentional and active response to water that your body makes, and it seems that the most widely accepted reason for this response is that the wrinkles improve our underwater grip by channeling water away. But let's not forget that we're making a video about cake. Whether it's osmosis or grip or some combination of both doesn't really matter to us because the mechanics of the wrinkling is the same. We have some thin film, that's your skin, and a substrate, that's your flesh or the meat in a prune, and these two materials have different levels of stiffness or they change volume differently, so the substrate becomes smaller relative to the film's surface area. The math problem is this: when that happens, what shape does the film make? Some solutions are obvious. For one, the film could be a sine wave. If you look at it from above, that would look like stripes. But another valid solution is that it gets crunched in the other direction too, so you get circular dents that are spaced out in a grid. If it gets crunched in three directions, it'll form dents in a hexagonal grid. These all solve the problem, but I've never seen any of those patterns naturally form in real life when something wrinkles. Maybe the sine wave is close to what sometimes happens, but it's never exact. Things don't wrinkle perfectly because the stress and the material are rarely perfectly homogeneous. These solutions don't explain the patterns that we see on our fingers, or on prunes, or on brains, or on tiger skin cake. In an attempt to model the wrinkles that form on curved surfaces, a 2015 study started with the same film substrate model that we looked at. They came up with an equation to give the height of the wrinkles once it's solved, but the interesting thing is that with the assumptions they made and the way they wrote it, this equation has been solved before, in a very different context. This is a variation of the Swift-Hohenberg equation, and it was first derived to explain convection. The surface of a fluid that's undergoing convection can make labyrinth-like patterns that we recognize as wrinkles. So using the Swift-Hohenberg equation, researchers demonstrated both analytically and in simulations that wrinkles on curved surfaces can form patterns that are either hexagonal or maze-like depending on the curvature and the amount of stress. The original question that I asked was, why does the cake look like this? And my hypothesis was Turing patterns. Let's look at a reaction-diffusion equation and a Swift-Hohenberg equation side by side. Reaction-diffusion equations are, in general, of multiple variables to handle multiple morphogens, so let's pretend there's only one chemical to make it look nice. Call me a conspiracy theorist, but I think that these are pretty similar in structure. They're both differential equations in time that involve the Laplacian or some higher order differential. Many of the terms are the same, up to a constant. And we've seen that there's a lot of leeway for choices of these functions too. As long as a system vaguely follows this formula, it'll be able to express the cool patterns. Interestingly enough, the connection between these two concepts has been noted before, and the Swift-Hohenberg equation has even appeared in literature as the Turing-Swift-Hohenberg equation. But here's where things come full circle. The reason for adding Turing's name in is not just because this equation looks kind of like reaction-diffusion. It's because we now know from unpublished manuscripts that in the last years of Turing's life, he derived what we call the Swift-Hohenberg equation, 23 years before Swift and Hohenberg. In every sense of the term, the pattern on tiger skin cake is a Turing pattern. It deserves his name because he discovered it, even though he wasn't necessarily thinking about its application to convection or wrinkles. So after all of this, we have a few possibilities for our cake. It could be a reaction-diffusion system. Some molecules in the egg yolk might react with the sugar to make some parts of the batter rise more than others. Or it could be mechanical wrinkling. The cornstarch changes the surface tension in such a way that the top layer expands more than the lower layers when it bakes. Or it could be convection. The batter is a liquid until it's baked, so maybe it moves around and bubbles while it's heating up. In all honesty, I don't know which one of these is causing the patterns. I think I'm leaning towards the wrinkling hypothesis, but I just don't have the background to say. Until some mathematically inclined food scientist or baking inclined mathematician makes this their PhD thesis, the world may never know. Although if you do come up with an explanation, please tell me. But better even than explaining it, I think we've made a more profound discovery about this cake. It doesn't matter. And I don't mean that it's not worth talking about. I mean, no matter what mechanism causes the patterns to form, the math is the same. We can rightfully call this a Turing pattern. Whether it's two chemicals on a plate, or fish skin, or Photoshop, or the human brain, or wet wrinkly fingers, or a rubber ball being deflated, or boiling soup, or clouds, or this fermenting wine I found on Wikipedia, or this blog post I found about watching paint dry, or tiger skin cake. Even the simplest of systems can lead to beautiful complexity.